Hello everybody. In this video we're going to be covering section 11.1, the dissolution process. Our learning objectives are going to be, first we're going to describe the basic properties of solutions and how they form. We're going to be able to predict whether a given mixture will yield a solution based on its molecular properties. And we're going to explain why some solutions either produce or absorb heat when they form. So first, let's get some of our vocabulary out of the way. So solutions are homogeneous mixtures of two or more substances. The solvent is the component of the solution with significantly higher concentration. So the majority of our solution is going to be the solvent. Solutes are components of the solution present in relatively smaller concentrations. So these are the smaller bits that we're going to add to our solvent in order to form a solution. When a solution forms, solute is distributed evenly throughout the solvent. We're pretty familiar with the idea of solutions, but we often think about this as just being solids dissolved in a liquid. But it's actually true that the components of a solution can be any phase. The classic example is just thinking of adding something to water and it dissolves. This is so common that we actually have a special name just for water-based solvents called aqueous solutions, and we have a little symbol, AQ, that we use for that. But alloys, for instance, are solid solutions of two metals. So one metal is actually dissolved in another, and it's in the solid phase. But it's still a solution. It still has these rules. Air is a solution of gases with a nitrogen solvent. Okay, so the largest component inside of air is nitrogen gas, and something like oxygen that we're breathing out of the air would be the solute in the nitrogen solvent. Here we have a table with a couple other different solution combinations that you could imagine, and you can see that they can combine in any sort of thing. So soft drinks, for instance, have CO2 gas in liquid water, hydrogen and palladium, so now we have a gas that's dissolved actually in a solid, and this is actually pretty special. This is one of the techniques that they've tried to use in order to capture hydrogen and store it for like use in fuel cells and stuff like that, trying to increase the hydrogen density. Rubbing alcohol typically contains some water dissolved in 2-propanol, so now we have a solution of two liquids. We have our classic like salt and water, so we have a solid dissolved in water. And then brass is a solution, an alloy between zinc and copper. So let's talk a bit about solution properties. As we said before, they're homogeneous, all right? And what that means is that after a solution is mixed, its composition is going to be uniform. That means that if I have a solution and I pick out any little bit of sample from it, it's going to be exactly the same and have the same distribution of molecules and atoms or ions as another sample that I picked out of it. The physical state of the solution is typically the same as that of the solvent. Okay, so if we have a liquid solvent, our solution is going to be a liquid. If we have a gas solvent, our solution is going to be a gas. The components of a solution are dispersed on a molecular scale. All right, so what that means is that we're going to see all of the molecules, atoms, and ions completely dispersed, and they're all going to have roughly the same distance from one another inside of our solution. We're not going to see like pockets where the solute molecules are bunching together, for instance. That's a different thing that we're going to talk about later called a colloid. They consist of a mixture of separated solute molecules, all right? And very key here is that the molecule, atoms, or ions are each surrounded by solvent species, okay? And that's the process that we call solvation that we're going to talk. A couple more solution properties to keep in mind. The dissolved solute in a solution will not settle out or separate from the solvent, okay? So if you think of something like mud or something like that, you could, shake it up so that it appeared to be homogeneous. But if you let a little time pass, then you would start to see the dirt settle down to the bottom, because that's not actually a true solution. The composition of a solution, or the concentrations of its components, can be varied continuously, which you might take for granted, that you can just add any arbitrary amount of, say, salt to water or something like that. But that's not always true if you don't have a solution. And that is actually only works within the limits of its solubility. So at some point when you are adding the salt, you would have what we call a saturated solution, and you wouldn't be able to add any more salt to it. You would have reached an upper limit of how much salt the water could hold. However, on the other side of that, very, very dilute solutions, typically you can make the solution just as dilute as you need to. So let's talk a bit about spontaneity, okay? The formation of a solution is a spontaneous process. This means that it's going to happen without the input of external energy. There's two ways that we get a spontaneous process, and we're going to have a whole chapter about that we're going to talk about. The first one is by having a decrease in the internal energy of the system. So energy is released from the system, meaning it's exothermic, which means that the enthalpy of that process is negative. The second is the increase in the dispersal of matter in the system. And mathematically, this means that our entropy, which we haven't discussed yet, is going to be positive. All right. This is typically always going to be true for a solution. This is often true. The majority of cases it's true, but does not necessarily have to be true. And we're going to talk about that a little bit more in a minute. Heating, and this is very important for you to understand, heating and stirring the solution may speed up the dissolution process, so it may make it happen faster, all right? But they're not necessary for it to happen. If I add salt to water and I stir it, it will dissolve faster, but if I just left it alone, it would have still dissolved eventually. Stirring can only speed up the dissolution. All right, it will not increase or decrease the amount of solute that can be dissolved. All right, I can stir the mixture over and over and over again, but I'm not going to be able to fit any more into it than I already would have been. That's not true for heating. Okay, heating can speed or slow the dissolution process, but it also affects the amount of solute dissolved. I can dissolve more salt in hot water than I can in cold water, for instance. Let's talk a bit about ideal solutions. So, as is often the case, it's nice to start with a model that's very, very simple in order to kind of conceptualize everything. And in this case, what we have is we have what we call ideal solutions. And they occur when the strength of the intermolecular forces of attraction between the solute and the solvent species are the same as the IMFs present in the separated components. All right. So if we go back to our idea of intermolecular forces being the stickiness of a molecule, what we're saying is that in a case like this one here, the helium atoms are just as likely to stick to one another as they are to stick to an argon atom. And the argon atoms are just as happy to stick to another argon atom as they are with the helium atom. All right. This means, because these intermolecular forces are the same, that there's not going to be any accompanying energy change in the reaction. Our delta H is going to be 0. So this whole dissolution process in this case is just being driven forward by the increase in randomness of the different components. All right. The argon is a very ordered system over here. The helium is a very ordered system over here. When we open the valve, they mix together. They increase the level of disorder that they have, and we wind up with a more chaotic system, which is favored thermodynamically. So ideal solutions typically are going to form when we have very structurally similar liquids. Okay. Some ideal solutions do experience intermolecular attractive forces. All right, so over here we had an example where we just had very weak intermolecular forces in general, but that doesn't necessarily need to be true. Okay, the intermolecular forces could be quite large. The key is that they are balanced. All right, so that the intermolecular forces between any one of these components is very similar to the intermolecular forces between the mixed components. So let's talk a little bit more about solvation and those intermolecular forces. When a solution is formed, 3 steps occur. All right. First, the solute attractions are overcome. This requires energy be entered into the system to break those intermolecular forces. Okay, so that's an endothermic process. It's going to require the input of energy. Then the solvent-solvent attractions need to be overcome. Again, an endothermic process. And then new attractions are going to form between the solvent and the solute. And that is the exothermic bit of it. Okay? So that means that when the intermolecular attractions between the solvent and the solute are larger, so these guys like to stick to one another more than the solvent and the solvent or the solute, then we're going to see a solution start to form. All right. The process of forming these solvent-solute attractions is called solvation. Solutions form when the energy released during solvation is greater than the energy required to overcome the solute-solute and solvent-solvent interactions. Let's take a look at a picture of that. Okay. So if you think about it, if we had them in 2 separate beakers, I have my solute here, I have my solvent here. The first thing I need to do is break this solute up so that it is evenly dispersed. The second step is that I need to break these guys up so that they're evenly dispersed. And then when I put them together, I form these new attractions between the different species. Okay? In actuality, these steps don't really occur, right? It's all happening in one concerted step. But we could imagine a world where we were actually able to move molecules and be able to make this happen and see that this 3-step process has to occur. So, as I said before, not all dissolution processes are exothermic. Some of them are endothermic. All right. It is possible to have these endothermic reactions, and these reactions are driven entirely by the increase in disorder caused by dissolution. All right. So we actually have to have a even larger increase in the disorder of the system to overcome the barrier of having to input energy to make the solvation happen. One of the classic examples of this is ammonium nitrate and water. This is an endothermic process. If you guys took Chem 131 with me, we did this in the lab. And this is our basic cold pack reaction. If you've ever seen these like medical cold packs, they have a little baggie of water in there. They have ammonium nitrate on the outside. You puncture the baggie by squeezing it. They start to mix, and the whole pack gets cold after that.